Hello and welcome back to Control System Lectures. Let's cover the highly requested topic of the Nyquist stability criterion, at least the first part. This is a topic that I can honestly say I didn't really get as an undergraduate student, but it turns out that I was just being lazy because the criterion is actually pretty easy to understand with just a small amount of concentrated effort. So let me explain it to you the way I understand it, and maybe with this video and some other textbooks and other videos on YouTube, you'll be able to create your own understanding of the criterion as well. But first things first, let's talk about what we're trying to accomplish by using the Nyquist stability criterion. Here is a typical open loop block diagram of plant G of S and control process H of S. You generally have both of these transfer functions for your system since you know the plant that you're trying to control and you get to pick the control process to control it. The open loop transfer function then just becomes G of S times H of S. But to save time in this video, I'm going to drop the of s's and just write G times H. When we close the loop, this physically adjusts the transfer function for the entire system, and you can reduce the block diagram into a closed loop transfer function, G divided by 1 plus G of H. So you can determine if your open loop system is stable by finding the poles of G times H. The poles are values of S that cause you to divide by 0 in the transfer function and so that the result blows up to infinity. If there's a pole in the right half plane, then the open loop transfer function is unstable. For the closed loop system, we're still looking for poles. However, you can see from the transfer function that in order to divide by 0, 1 plus GH would have to equal 0. Therefore, we can check stability of the closed loop system by looking at the location of the zeros in 1 plus GH. This might get a little confusing because I might accidentally say, we need to check for closed loop stability by looking at the location of the zeros. But what I really mean is that just the locations of the zeros of 1 plus GH. So just keep that in mind as we move forward. So all we're really trying to do is find where the zeros are of 1 plus GH, or take the open loop transfer function, add 1 to it, and then find the location of the zeros. Why is this so difficult? Well, for one thing, if your open loop system is high order, let's say 50 poles or something, then finding the roots of that large 50th order equation can be difficult by hand. Of course, now we have computers, so that isn't a big deal. But even so, all you would have is stability information, and no other useful information like stability margins. So let me show you something real quick in MATLAB. I'll just generate a random transfer function called sys. I'll plot the locations of the poles and zeros for this open loop system. And then right next to it, I'm going to plot the poles and zeros of 1 plus the open loop system. So here you can see how the zeros in the right graph are not obviously related to the poles in the open loop system in the left graph. That's because when we add 1 to the open loop system, it can really move the poles and zeros around. However, let's generate the Nyquist plot for G times H and 1 plus G times H. Hey, this kind of looks like Mickey Mouse randomly. Anyway, isn't this much simpler looking? All we're doing is adding 1 and just shifting it over. So adding 1 to the open loop transfer function and trying to find the pole 0 locations is hard graphically, but adding 1 to a Nyquist plot is really easy to do. Now the only thing we need to know is how to determine stability and stability margins from this graph of squiggly lines. And once we know that, then we're golden. Luckily, it's pretty straightforward once you know what to look for. But before I tell you that, I first want to show you how this plot is generated. And in doing so, I think reading it and determining stability will become obvious. To start, we need to discuss Cauchy's argument principle. Let's say that we have this arbitrary transfer function, s plus 2 over s plus 1. And I'll put the s-plane on the left here and mark the locations of the poles and zeros for our transfer function. There's a pole at minus 1 and a 0 at minus 2. Now if we take just a single point in the s-plane, let's say s equals minus 1 plus j, and plug it into our transfer function, which is s plus 2 over s plus 1, you'll get a new complex number out, 1 minus j. And let me plot this new complex number on a new plane that I'm just going to give an arbitrary letter w, the w plane. This process of plugging in one complex number in the s-plane and getting a new complex number in the w-plane is called mapping. So the transfer function maps a point from the s-plane to a different point in the w-plane. And if we add a second S point near the first, we're going to get a second point somewhere else on the W plane. And if we plugged in more and more points on the S plane as to form a continuous line, then this will form a continuous line in the W plane. And if you draw a continuous line that connects back to itself, we call this a contour. And it'll generate some sort of continuous squiggly line over in the W plane that also connects back up with itself. We're going to call this line in the W plane a plot. Except that squiggly line isn't just random gibberish. It actually contains the phase and magnitude information from each of the system's poles and zeros. Let me explain it in the following way, using just a small amount of math. But really concentrate on the idea rather than the math if you find it confusing. I'll simplify our transfer function just a bit for this example, down to a single zero at s equals -2. And I'll map the point s equals -1 plus j over to the W plane using our transfer function s plus 2 over 1. And we find it to be 1 plus j. Now here's the really interesting part. The phasor of the point in the W plane is exactly the same as the phasor between the 0 and the point we chose in the S plane. And this concept extends to multiple poles and zeros as well. And what's nice is that you can figure out the mapping between the S plane and the W plane graphically. I'll show you how in this set of 3 poles and 2 zeros. Step 1 is to pick the point in the S plane that you want to map over to the W plane. Step 2 is to draw the phasors from each of the poles and zeros to that point. Step 3 is to determine the magnitude, or the length of the phasor, by multiplying all of the zero phasor magnitudes and dividing out all of the pole phasor magnitudes. This resulting magnitude sets the length of the phasor in the W plane. Step 4 is to determine the phase by adding the phase of all of the zeros and subtracting the phase of all of the poles. So in our case, we'd add the 2 blue angles, subtract all of the orange ones, which just by eyeballing it looks like the phase would be just greater than 90 degrees, and so it would be here in the W plane. So you might be wondering why I'm telling you all this. We aren't going to be doing this mapping graphically in general, since it's usually easier just to plug in the point and solve the equation. However, understanding what is happening in a graphical sense is going to help us interpret the plot later on. Let me show you what I mean using MATLAB again. I wrote a small program in MATLAB to give you a visualization of what I just drew for you. Here we have a transfer function with 2 poles and 1 zero. You see the exact function in the title. I've chosen a value of s right in the middle at s equals -2. And on the right is the mapping of that point into the W plane. You can see very quickly that if we add the phase of the 0, which is 180 degrees, and subtract the phases from the poles, which is positive and negative of the same angle, so they cancel each other out, that the phase should be 180 degrees on the point on the right. And it is. Now let me move this point to a new spot in the S plane. Now the phase from the 0 is plus 90 degrees, and the phase from the pole is maybe around 60 degrees or so. And therefore, 90 minus 60 is about 30 degrees, and that's again what we see of the point in the W plane. Now if I sort of trace out a contour with this point, but make sure not to include any pole or zero, then the addition and subtraction of the phases will never go around 360 degrees. And you can see this very clearly on the W plot, that the phase just sort of hovers between 150 degrees and 210 degrees. However, if I do encircle a 0, then as we go along the contour in a clockwise direction, we'll be adding 360 degrees of phase as we move around the 0. This causes the point in the W plane to rotate 360 degrees in a clockwise direction like our contour. And if I circle a pole, then we're subtracting 360 degrees of phase as we move around the pole, causing a counterclockwise rotation in the W plane. Now, I've written a second demo that might make this a little bit easier to see. Here I have a single pole that I encircle, and the resulting plot circles the origin one time in the counterclockwise direction since we're subtracting 360 degrees of phase. Now I'll add a second pole and rerun it. And as you can see, there's going to be 2 rotations around the origin, one for each pole. Finally, I'm going to add 2 zeros as well. And now the resulting plot doesn't circle the origin at all. And that's because we're adding 2 times 360 degrees of phase from the two zeros, but at the same time subtracting 2 times 360 degrees of phase from the two poles. Sure, the plot on the right, which is the green line, is still going to have a bunch of circles and squiggles in it, but it never encircles the origin, which is really important to note. And that is really all you need to know for Cauchy's argument principle, that you can tell the relative difference between the number of poles and zeros inside of a contour by how many times the plot circles the origin and in which direction. So let's see, if I gave you this arbitrary contour and then told you that the mapping into the W-plane looked like this, what could you tell me about what's inside? Well, let's see, it circles the origin once in the clockwise direction, so there must be 1 0 inside the contour, right? Wrong. Well, sort of wrong. Remember, all this tells us is that there is one more 0 than poles inside the contour. So if there are no poles, then there is 1 0. But what if there's 3 poles? Then there must be 4 zeros. Now let's take a new contour, and if I said that the mapping looked like this, where it encircled the origin twice in the counterclockwise direction, well, then you would say that there are 2 more poles than zeros. And if we knew that there were only 2 poles to begin with, then we could confidently say that there were no zeros in this contour. In order to figure out how this information helps us, let's get back to our problem. We're trying to figure out if there are any zeros in the right half plane for 1 plus GH, because if there are, that means that the closed loop system is unstable. And now we know how to use Cauchy's argument principle to determine if there are any zeros inside of a contour. So at this point, it should be obvious that if we want to see if there's any zeros in the right half plane, then we need a contour that encloses the entire right half plane. And we do that by saying that the contour runs the entire length of the j omega axis up to positive j infinity, and then it sweeps around at infinity to enclose the entire right half plane, and then goes back up the negative j omega line back to 0. Now if there are any zeros in the right half plane, we're going to know about them. This is called the Nyquist contour. All those other contours we drew didn't have a name, so maybe I'll call one like the Douglas contour or something. But when you map the Nyquist contour into the W-plane, you get what's called the Nyquist plot. It's all those squiggly graphs I plotted in MATLAB earlier. And again, you get those plots by plugging in every single value along the j omega axis and then all the points along infinity in the right half plane. This is easier to do than you might imagine, but I'm going to cover that in the next video. For now, we'll rely on the computing power of MATLAB to generate those plots for us. So now if we take 1 plus GH, and use this function to map the Nyquist contour in the S-plane into a Nyquist plot in the W-plane, we can instantly see how many times the origin is circled and in which direction. From there, we can determine how many more poles or zeros lie within the contour. To do this mapping, though, we need to find the plot for GH and then shift the entire plot to the right by 1. But this is kind of difficult because there's lots of curves and circles. So instead of shifting the plot to the right by 1, we shift the origin to the left by 1. And this is why we're concerned with how many times minus 1 is circled instead of how many times the origin is circled. So the steps are that we take the open loop transfer function, GH, we make a Nyquist plot by plugging in each point on the Nyquist contour and count the number of times minus 1 is encircled and in which direction. From that, we can determine how many more poles or zeros are inside of the Nyquist contour, which again is the entire right half plane. But to know for sure whether there's a 0 in the right half plane, we first need to know how many poles are in the right half plane. Luckily, we usually know exactly how many poles are in the right half plane of 1 plus GH because it's the exact same number of poles in the right half plane as the open loop system GH. And since we usually have a good understanding of our open loop plant, then we already have that information. And this drives the famous equation that the number of zeros in the right half plane, z, is equal to the number of clockwise encirclements of minus 1 plus the number of open loop right half plane poles. Or another way of saying this is that in order to guarantee there are no zeros in the right half plane, then you better have exactly 1 counterclockwise encirclement for every open loop pole in the right half plane. Any less than that, and you know you have at least one right half plane zero messing things up. So one very important bit of information you should be taking away from this is that if someone gives you a Nyquist plot and asks you to tell them how many zeros are in the right half plane of 1 plus GH, you can't unless you know a little information about the open loop system, GH, namely how many unstable poles there are. Now, one thing that sets Nyquist plots apart from Bode plots in terms of determining closed loop stability is that with Nyquist, you have the ability to analyze a system with an unstable open loop plant. If you try to determine closed loop stability of an unstable open loop plant with Bode, you're going to be out of luck, because you'll possibly come away with the wrong answer and not know it. There are also other examples of other types of systems that will confuse you in Bode plot form, but will always work perfectly in Nyquist form. Bode plots are nice because they're easy to sketch by hand. However, if you have access to a computer, you won't go wrong if you always use Nyquist plots to determine stability and stability margins, and then just use Bode plots for frequency response analysis. So this is all I wanted to cover in part 1 of the Nyquist stability criterion. In the next video, I'm going to explain what to do when your open loop plant has a pole or two on the j-omega axis, and also how to determine phase and gain margins directly from the Nyquist plot. Plus, I'll give you a few examples. Now, if you have any questions or comments, please leave them below and I'll try to answer them if I can. Subscribe so you don't miss any future videos, and as always, thanks for watching.